Welcome friends. Let's start with the new topic, that is the bending stress. What exactly the bending stress is, how it can be defined. Actually, the internal stresses developed in the beam are known as the bending stress or the flexural stress. So to understand this, we need to draw a diagram, a figure. So let me draw the diagram first. Here is it in the figure. Here it is displayed. The portion CD of the simply supported beam is under pure bending, as there exists no shear force. If the ends of the section of a straight beam are considered to remain plane, so the beam under the action of bending moment bends in such a way that the inner or the concave edge of the cross section undergoes compression. So if we will apply this load here, so this cross section will undergo like a concave surface. So let me draw a three-dimensional structure of that, then you will easily understand about this step. So here it is, the three-dimensional structure that I've drawn here. So this particular part, the the concave edge of the cross section undergoes the compression. So here it is compression, and on the bottom part it will feel some it is a tensile side. So this is the compression side, this is the tensile side. Okay. So uh, there is an intermediate surface also. This particular surface will somehow elongated. So we have considered that this will be the tensile side, and this is somehow compressed, so we have considered that this is the compression side. So in between these two surfaces we will consider a particular surface in middle the beam, in the middle of the beam. So that will be that axis will be known as the neutral axis, and the surface is known as the neutral surface. Okay, so where the neutral surface is, so the stress is zero. So in the neutral surface the stress will be zero, and a cross section of that is known as the neutral axis. Okay, so about which the bending of the surface takes place. So for the relationship between the bending stress and the radius of curvature, consider an element. Let's say it is an element of length AB. We can consider this part as A and this part as B of the beam. So this is an beam, and we are considering the part AB of the beam as shown in the figure. So let E, this point we may assume as this is our E, and this is F, this is G H. This part we may consider as CD. Okay, so let EF be the neutral layer and CD the bottommost layer. If GH is the layer at distance y from the neutral layer or the neutral axis. So if we have considered this as neutral axis EF, so this particular layer at a distance small y, we can say this as the small y distance in between these two layers. So the bottommost layer, okay, is this one. The CD is the bottommost layer, and if GH is a layer at a distance y, So this we have considered from the neutral axis EF. So initially what is the condition? AB is equals EF is equals GH is equals CD. So this is the initial condition. So if let's say after bending, so what kind of the bending will be? Let me draw some another direction. So this is without bending. When it will be bent, so somehow the structure will be either concaved or the convex surface, lower and the upper surfaces respectively. So we can say here, if this is our beam now, okay, so we can say, let me draw it clearly. So now this is our beam after the bending. So this was now A dash, so it is our F dash, H dash, and the distance is Y in between this. So here it is E dash and G dash. Okay, so now after the bending, the points A, B, C, D, E, F, G, and H takes positions like A dash, B dash, C dash, D dash, E dash, F dash, G dash, and H dash. Okay, let's see this. This is point O. We can say, so this angle is phi. So and it will form an arc of the circle up to this point. So the radius up to this point can be represented by capital R. Okay, so initially we know that neutral, at the neutral axis, that is our EF, it will be, remain same. So EF is equals E dash and F dash, we know. Okay, so let me raise this, make some space on the board so that we can proceed further. So here is the neutral axis, we can say. So that is what EF is equals EF dash, since EF is our neutral axis in the previous diagram also. So if this is our neutral axis, so it will be equals to the R phi. So we can say that EF is equals capital R phi. Okay, and the strain in GH, that will be in this lower uh, surface, lower part of this beam. So here it is a distance of small y from this part to this part. So what will be the radius now? It's R plus y. So it's R plus y into phi is the final the value of this part. Okay, so we can say the strain, that is final minus initial. So directly I am putting here the values. So that is R plus y phi minus the initial length. This is our final length after the elongation, and initially it was up equals to the neutral axis. Okay, and that divided by the initial length. So that is our R phi. So this you can represent as equation number 1. Okay, so what exactly this value is on solving, either you can say, first we will solve this equation. So that will be, it is R phi plus k y phi minus R phi upon R phi. So this term will be cancelled out, and phi will also cancelled out. So it is y upon R. So this is our equation number 1. Since the strain in the GH is due to the tensile force, so we can say the strain is equals to what, that is the tensile, we can say the strain can be its F over E, that is our equation number 2. As we know, where E is what, E is the modulus of elasticity. E is the of modulus of elasticity is this one. So because you know that that is equals to stress upon strain is equals E, so directly we are putting this value here. So by equation number 1 and 2, both are the strain, we can put that F upon E is equals Y upon R. Okay, so here this R is, you know what is this, and E is the modulus of elasticity, R is the radius of this part, or the curvature, and Y is the elongation part. Here F is our the force. Okay, so stress we can say, uh, uh, that is our bending stress here in this term. So we can say this is our equation number 3rd. So now to find the relationship between the bending moment and the radius of curvature, we need to draw some another diagram. So let me draw it first. It's a relationship between the bending moment and the radius of curvature. So for that, consider an elemental area. If this was our initially in my previous diagram, so this is the neutral axis. So let us consider an elemental area. If let's say this is the structure, so this is the curvature part. So if here it is the neutral axis, and at a distance of small y from this neutral axis, let's see here it is in uh, part as represented delta a. Okay, this part. So consider an elemental area delta a at distance y, uh, at this distance y from the neutral axis as shown in the figure. So from equation number 3rd, we know that F upon y is equals E upon R. Either we can say that F is equals E upon R y. Okay, so the force on this element is force on this element, that is equals to E upon R y delta A. Okay, on this element we have calculated the force. So what will be the moment of resistance of this elemental force about the neutral axis? So for that we need to multiply by this particular distance in this equation. So the moment of resistance of this force, of this elemental force, we can say force about neutral axis. So that is equals to this part multiplied by the y. So it is E upon R into y into delta A into y. So that can be written as its y square delta A. So this is our equation number 4 now. Okay, so now I think it is visible to you. Okay, so now instead of this particular section, or this elemental area delta A, if we want the total moment the total moment resisted by the section. So that can be the sum of all the moments due to the different parts. So we can represent it as m dash, that is sum of E upon R, this particular term. So it's y square delta A, or we can also write it as it is E by R sum of y square del A. So from the definition of moment of inertia, the second moment of area about the centroidal axis, we know that is simply uh, I, that is sigma y square del A. So in place of this particular term here in this equation, we can write like I. So M is now it's E by R into I. Either we can say from equilibrium condition. So this was M dash. So from like equilibrium condition, M is M dash. Okay, where M is the applied moment. M is the applied moment. So we can say, we can write it here finally as M is equals E upon R I, or M upon I is equals E by R. Okay, and in our equation number third, we have calculated the relation between that. So we can finally conclude that M upon I is equals E upon R is equals F upon Y. So Y. Okay, so this is our equation number, I think 5, and this is question number 6. Okay, so what are the variables can be represented as M is our bending moment at this section, I is the moment of inertia about the centroidal axis, E is the modulus of elasticity, R is the radius of curvature for the bent section, and F is the bending stress, and Y is the distance of the fiber from the neutral axis. Okay, so this is the relation between the bending moment and the radius of curvature. Thank you, thanks for listening.